Okay, welcome to our seminar, How to Achieve Sustainability Using Heat Pumps with Johnson Controls. Our speaker today is Morten, Morten Deding, Director for Heat Pump Applications at Johnson Controls. My name is Michael Gary. I'll be moderating the session. I'm from Atmosphere, Head of Content. So we have this topic of heat pumps, of course, is very timely and very exciting because of all the interest in decarbonization and getting out of fossil fuels and moving into heat pumps. So we're going to hear a lot about that today. Before I turn it over to Morten, a little bit about him. He's Director for Heat Pump Applications and has over 20 years of industrial refrigeration experience. He has been in the consultant, product, and project manager roles in his career and is now using that experience to influence the adoption of heat pumps, supporting electrification and decarbonization of the heating sector. Over the last decade, he has been an entrepreneur in industrial heat pumps, resulting in more than 300 units and over 300 megawatts of installed capacity. He's dedicated to go over 100 degrees centigrade on double-digit megawatt heat pumps in the next decade. Morten has 2 degrees in engineering and an MBA, and his passion is enabling energy savings, utilization of waste heat, and renewals in heat pumps. So with that, I will turn it over to Morten. I would just first like to also remind our audience, you can ask questions by typing them into the Q&A box at the bottom or raising your hand, and I will call on you, be able to directly ask the question when we get to that part after the presentation. Over to you, Morten.
Yeah, thank you. And thanks for the opportunity to be able to speak to all of you here tonight. For some reason, I'm joining the North American session, and I think that fits well with an American company. I'm based in Europe, and so I have all night. It's actually 10 o'clock here, so I will share my screen, and then I will start my presentation. Yeah, and I think afterwards the presentation will be available also for you to download. Yeah. The topic of today is sustainability achieved by enabling heat pumps and by means of heat pumps. And just to give you some context around heat pumps and the Johnson Controls. I think you're all familiar with Johnson Controls, but at the end of the day, Johnson Controls is maybe not that known for its industrial part. I have been more than 20, actually, just reflecting today, 23 years in industrial refrigeration, and for the majority of my experience with Johnson Controls and with consultancies, we are a leading supplier of refrigeration, industrial refrigeration equipment. It's predominantly in Europe, based on reciprocating or screw compressor chillers, and if you look at what the market is, our market is predominantly food and beverage. But in the last 10 years, and I have been this time in my career 10 years with Johnson Controls, the utility. The utility and other industries are adapting. So we are kind of more or less flat in food and beverage and have expanded our business, selling heat pumps into utility companies. Johnson Controls in Europe is 1,600 people. It's over 900 technicians, and that's actually, we have our own facilities of manufacturing. And this footprint is actually enabled us to sell heat pumps, because when you sell heat pumps, you all of a sudden selling, if it's to district heating or utility companies, you're selling not an asset. You're actually selling the production equipment, and that's where heat pumps distinguish from traditional refrigeration. Equipment, my references in Europe is predominantly the natural refrigerants. I am a natural refrigerant engineer by heart. I have also learned about synthetics, but the business in Europe is for heat pumps has over the last many years been around natural refrigerants. Okay, so that was actually just to build up why my background of doing this webinar today. And as Michael said, over the last 10 years, actually more than 10 years ago, I saw the opportunity of starting to implement heat pumps with the customer when I was a consultant. There were some first mover projects and some pilot customers with sustainable image back then. I was so fortunate to have as customers. But it was tough it was tough 12 years ago selling heat pumps with fossil fuel still being inexpensive, or electricity being expensive, no matter how you do it. But we have grown, and in the last 10 years, more than 300 megawatts have been installed. And why was it so difficult? It was difficult because in the old days, electricity was expensive, fossil fuel was inexpensive. And it is actually the market drivers today that in Europe drives the sustainability agenda. It's European Union very much looks like United States of America in many ways, with our 28 membership states. We are looking at a sustainability transformation by electrification of the heating sector. And that has reformed, that is a reform called the European Big Deal. So there's a lot of market drivers. There's also a lot of CSR strategy among the large companies in Europe, not only utility companies, but also our traditional food and beverage companies, breweries, confectionaries, and abattoir and dairy breweries globally are looking. And another thing is the future taxation on carbon. Very sad about the situation in Ukraine, but at the end of the day, that might also have a significant importance as a lot of the electricity and also a lot of the heat in Europe stems from natural gas imported, and it's not that Europe don't have their own natural gas. I think it's maybe cheaper to purchase it from Russia, but that will be an unfortunate positive impact on heat pumps. Anyway, when you do heat pumps, it's all about the business case, and in this case, I have set euros or dollars. Same, but different almost. I think it's 17% more expensive. So if gas cost is 33 euros and electricity cost is 65, and I calculate in megawatt hours, then I have a ratio between the fuel cost and the electricity cost of 1.97 to be specific. If I, in this case, have a realistic COP of a heat pump, meaning that I can produce 3 kilowatts of heat for each kilowatt of electricity, I actually have a business case. I will have a 33% savings on energy costs. That's the running costs. So that's the first thing you need to assess. And that is why I have taken in this map that you see over here on the right, because that's very, very different from country to country. And as we progress, it's also different on other topics like CO2 emission from electricity production and all that. But at the end of the day, you start with if the COP is bigger than the ratio between your electricity cost and your gas cost, you have a business case. And that is the case that actually have moved the heat pumps from being a blue ocean market boiling with opportunities to now go into maturity with rapid growth, actually CAGRs between double-digit CAGRs over the last 5 years. So very extreme growth in heat pumps. So the pivot where the realistic COP is bigger than the ratio has now pivoted over in favor of the heat pumps in many cases. The difference, but it's also very important to say that what is a difference between a boiler? A boiler is very responsive. It's not very strongly dependent on the temperatures in the heating system, because the flame is very, very hot. So if the water in the boiler is 80 or 90 or 70, there's still a big pinch up to the actual temperature where you have the fuel. A heat pump, on the other hand, is actually a thermodynamic equilibrium between two sides. So here the efficiency is strongly dependent on what are the difference from the cold side from the hot side. A heat pump is pulling a coefficient of performance, meaning you utilize some waste energy or some renewable energy. You use the electricity in the compressor, and you end out with an energy output that is the sum of the waste energy or renewable plus the electricity with a very, very high efficiency. But the input in electricity and what you can utilize in the waste heat is strongly dependent. And it also affects the business case, because are we going from a low temperature, 55 is like the hot water tap, you can actually use standard equipment, ammonia equipment, 28 bar, fairly inexpensive. We have tons of it in industrial ref for the food and beverage industry. But if we want to achieve higher temperatures like 75, that could be a trace 75 Celsius. That's a trace water system. You then increase into high pressure equipment or medium pressure equipment, 52, 40, 52 bar equipment, and the price increase is 30 to 50%, because we don't produce as many compressors. We have to change the steel from cast iron to steel casting, and sensors, gauges, valves, and all that increase. If you are going to 95 or almost to 100 to the boiling point of water, we are up in 60 bar, 63 bar, and then the price index is compared to 55 degrees or tap water temperature. It's 70% to double the price. And it also increases the complexity of the heat pump. I was just giving 2 examples. If we are going low temperature lift, we are going single stage. That's the illustration on the left. If we are going high lift from low temperature to 95 or boiling point, we are using a 2-stage and intermediate cooling and economizers, and so the complexity also increase. So the thing here is, A boiler is not heavily dependent on the temperatures in the heating system. A heat pump, and especially the price of the heat pump, is very dependent. So what about the efficiency? And I just want to give you some heads up here. I've made an illustration here, and it could be any odd heat pump. It could be any ammonia heat pump. It could be any odd manufacturer. If we claim the waste energy at 10 degrees Celsius, and we have a hot water side that is 40, 80, 85, 40 Celsius, our trace water system. And that could be a trace water system for a brewery, for pasteurs, or for cleaning water in an abattoir. It could be washing. If we go from 10 degrees to 85, a heat pump will produce 775 for the one in the picture. If we instead connect it at 40 degrees, and that could be utilizing waste heat from our refrigeration plant, all of a sudden we have the exact same machine, the exact same investment will almost double in capacity, but the efficiency, so the factor will go from performance will go from 2.8 to 4.5. Just to tell that a heat pump is heavily dependent on where we take the heat, from where we reclaim the heat, the waste heat or renewable, and pump it to the high temperature. On the other hand, also, if we have possibilities to optimize our trace water system and lower the inlet temperature from 85 down to 65, and that could be by optimizing, it could be by installing bigger coils in our air handling units, it could be our radiators in the office, and so on. We could actually achieve a 30% more efficiency on a heat pump, roughly the same capacity, but as efficiency increase. So just to highlight that it is really important that we to think about the business case is not only dependent on it's also what's available. I've tried here just to highlight some different sources. It could be air, it could be water, it could be soil or ground source, or it could be waste heat. And this is just examples. If you want to lift from here from 50 to 90, you would achieve 5.7 in COP. If you, on the other hand, go from -10 to +65, and that could be a ambient air heat pump, it's 2.8. These are just rule of thumb. There's many different scenarios, but just to your takeaway here is, as you increase your source temperature, your COP increase. As you reduce your trace water temperature, the COP increase. So what is then the sustainable saving? Because it's not only the energy cost. The energy cost is really important. But given the change in, so for the last many years, I've been selling heat pumps on the energy savings, and it's still nice to have a good business case. That's always nice. But what also is becoming evident is that CO2 footprint, the tons per year, is also important. And in many cases in Europe, it's associated with the monetary value. Large companies actually pay for their carbon footprint. So here I have made a sustainability calculation. So you take away some boiler fuel, you substitute a boiler fuel with electricity. And an illustration here on the right, I know this slide is busy, But if you are using, for instance, coal as a mean of producing electricity, and you have a plant efficiency of 39%, that is fairly average, there's a CO2 emission of 1,000 or 1 kilo per kilowatt hour electricity. But if, on the other hand, you go to countries like Norway, Sweden, who more or less do all their electricity on hydropower, then it's renewable electricity and the footprint is zero. So when you are calculating the CO2 savings, it's really also significant to the saving what kind of electricity you are actually buying, and many companies are buying renewable electricity from wind turbines or from solar but in this case here, I just take a heat pump with a COP of 4, a capacity of 1,000 kilowatts, 5,000 full running hours a year, meaning 5,000 megawatt hours, running on CO2 electricity that is from renewable electricity and substituting natural gas. A heat pump here in this case would save 1,000 tons of CO2 per year. Had it been high carbon electricity, like we used in many years in Denmark, the CO2 savings would only have been 49 tons. And just to put it in perspective, I think the average European have a footprint of 7 tons per year. I think the average human on the planet Earth has a footprint of maybe 4.5. So it's actually significant if it's either like in Europe, 7 people, or actually corresponds to 7 people if it's 49, or significantly more when it's like 150 if it's renewable electricity. So when you're doing the sustainability calculation, it's also important to know what is your footprint from the where you purchase your electricity. On the other side, there's also another added benefit here, because waste heat, especially waste heat in the food and beverage industry, is in many cases coming from heat rejection. And that could be heat rejection from a process industry with a evaporative condenser or a cooling tower, or an air-cooled condenser, or an air-cooled a dry cooler. And when you utilize the waste heat that goes into evaporation, or you utilize what goes into the dry cooler, you actually save electricity. And if it's evaporative, you also save water. And a capacity of 1,000 kilowatts on a that's like it's for each kilowatt, 1,000 kilowatts of capacity you take away from an evaporative condenser, you actually save 1,800 kilos of water per hour. So that's 1.8 cubic meter of water per hour. That's almost 2 tons. And you also save for the fans 30 kilowatts. If it's a dry cooler or an air-cooled condenser, you achieve only electrical saving. There's, of course, no water usage. But this is significant, and I have some examples. So how do I approach it? I have a factory here, and it could be a factory, it could It could also be a waste heat from a neighbor. But in this case, it could be a confectionery factory or an abattoir. They use some chill water. They have some cold stores and process where they use -10, -21, and for real cold storage, -40 when they're freezing in the products. It could be convenience products coming out of the oven, frozen down at -40 into the cold storage. These refrigeration plants generate some evaporative condensing energy. I also have an air compressor, and an air compressor, the potential is like 80–90% of the electricity you can actually reclaim waste heat. I also have some energy that goes out of could be boilers, it could be economizers, flue gas stacks from process stacks, high, hot, humid stacks that I can either condense or cool down. Process stacks, high temperature waste heat before from air handling units before it's released. Also have effluent water leaving from cleaning, from washing processes. And then again, I have energy going into the factory, like refrigeration. I have energy from hot water, trace water systems and hot water systems. This is just an example, but what I'm doing is I'm mapping it in a very old-fashioned pinch temperature diagram. Here I have the process is energy in, energy out. Here I have the cold, the chilled water, +4, +8. I have the heat rejection of the cooling plant, 30, 35 Celsius. In this case, these energy streams have a potential from a heat pump to be lifted to 65, 85, or 90. I actually also have a potential of free cooling where I can use tap water. I could use it to condense ammonia in the refrigeration plant before I push it into my hot water system. That's a complete no-brainer. I don't have to buy a heat pump. It's just a heat exchanger. So I map this for sites, each sites. That could be storage vessels involved. So there's not only the kilowatts, but it's also the availability of the heat during the day, during the process, that you have to take into account. But all these potentials here all accommodate for a potential implementation of a heat pump. So here, if we look at just to give it, I have named the following examples. I have a potential of utilizing waste heat going into 50, 60, 80, and that's the examples 1, 2, and 3. There's also, like I said, the opportunity to use wastewater and take the wastewater and move that into to the same temperature sets here. I will call this my secondary energy streams, and here are flue gas from boilers or high temperature stacks. That's also the possibility. So just some examples. Here is a screw compressor. It's a 2500 kilowatt screw compressor. I now combine I use as a source the chill water system. So here I do 12-degree, cool it down to 8 Celsius, and I heat up water from 40 to 50. That could be a low temperature trace system in a confectionery factory, as an example. In this case, I don't buy a heat pump. I don't buy a chiller. The machine is actually providing simultaneous heating and cooling, because I take it from the low temperature, I put it away at a high temperature. So I get, for each kilowatt of electricity, I get 3.7 kilowatts of cooling. But on top, I also get 4.7 kilowatts of heating. So here I actually combined almost get 8 kilowatts of energy, hot and cold, out for each kilowatt of electricity. If I move downwards in temperature, low temperature chill water system for 8 to 4 degrees Celsius, of course the COP drops, as I said. If we increase the lift, we also, but again, it saves actually a significant amount of energy replacing and again here, another example, again, a chill water source where I use the cold side, put it into the hot side. Again here, it's not a heat pump, it's not a chiller, it's actually both at the same time. And again, I can achieve significant CO2 savings in tons per year on equipment. And I can combine, if I can use the heating and cooling at the same time, the heating I can store in vessels. If I can save it later in a brewery for cleaning, in a dairy, on an abattoir, you use the heat at night for when you clean up the production. But I actually get a really good COP. And if I don't have any more heat to store in the vessels, or I cannot use it, I can always connect it to the evaporative condenser, and then it's just a simple chiller. So here the potentials are really big. I have an example here, and this is a data center, and it's a data center that is 50,000 square meters. It has a heating capacity of up to 27 megawatts, and it's actually utilizing waste heat from a data center. And it's only one of multiple data centers at this site, but it provides actually heat corresponding to 7,000 homes. It's providing heat, and a modern data center is utilizing evaporative cooling or adiabatic cooling in many cases. But utilizing the heat and putting it into a district heating system actually saves 360 tons of water per day and 17,000 tons of CO2 that was put in by natural gas, as an example, into the district heating. So here, utilizing the waste heat from a data center makes so much sense. And these data centers, the number of them will increase, and if you place them here, like in the picture, in an urbanized area, you can actually use the waste heat from a data center and use it to power up your modern city. I've put another system here. It could be a data center, but could also be a cooling tower, reclaiming the waste heat at 30, 35 Celsius, and that's a fair or normal temperature for for a chiller. Here again, a heat pump capacity, a chiller capacity of 1350 kilowatts, pushing it low temperature heat with a COP of 8, and the ratio, as I said, was like 3. So it's in Europe at the moment. So here it's really a big business case. We can try and move it a bit up in temperature. Now we are doing 60, 65 Celsius inlet. The COP drops a bit. 6.2 is still good. A bit less. I have tried to take a winter example here where the evaporative goes down to 20, the source, but still a significant savings here, 1,000 tons a year. And here, what really is interested, and now you see the complexity of the machine also increase. I'll try to put that in the picture. Now we are going into 2-stage compression. Still a COP heating of 3.75, still a significant saving of CO2 of 1,770 tons a year. But again, the COP drops, the complexity of the equipment increase, but still, if we do it clever, we have a ratio, a COP that is bigger than the ratio between the fuel and electricity cost to make a business case. Yes. Here, yeah, same. It's a screw compressor for large capacities. This is an example, and it's actually taken from Danfoss' own communication. It's an old story. It was one of the pioneers here doing plastic molding. The energy was from the molds were the waste heat from the cooling of the plastic mold was released into evaporative towers. But instead of putting it into evaporative towers, we are actually cooling it down with a heat pump from 26 to 22 Celsius and pushing a hot side from 50 to 80. 2 megawatts, 4.2 in COP. And if we had used renewable electricity and low carbon natural gas, this unit saves Danfoss 1,500 tons of CO2 and 35 tons of water per day. Yeah, very quick. The last one, the secondary waste streams from wastewater. Wastewater from wastewater treatment plants traditionally comes at 25 Celsius during the summer, down to 16 degrees Celsius in the winter. And it's actually, effluent water is almost clean when it leaves the effluent station. And in many cases, when we use ammonia, we put in a safety circuit. You could also use dual pipe heat exchangers, shell and tube. They're not that common. They are very expensive. So in many cases, we put in a safety circuit. Even though we put in a safety circuit, you can see now that the COP begins to reach the pivot point. But it's still, in many cases, it's still a really good business case, because this is the source temperature, maybe in a design situation, but on average, it can be achieve higher over the year, running in different scenarios. But waste heat from effluent water is really a source that we see like 30% of all projects in Europe. I've taken another example. One of Johnson Controls' dear customers was so fortunate to win European Heat Pump Association's award this year, last year. And that's an office building placed in Trondheim, and that's actually only a few hundred kilometers from the Northern Hemisphere. So here, how is that achievable? An office building covered in solar panels, actually producing 500,000 kilowatts of electricity per year, using roughly half for power for lights and computers. So half of it left for heating purposes. So by doing an ammonia heat pump and a low temperature trace water system for heating the building, utilizing the seawater here, ammonia directly into the seawater, and low temperature heating system, a cumulative accumulating heat in the concrete structure. This building, placed in a few hundred kilometers in Trondheim from the hemisphere, is an energy positive building. It's producing more electricity per year than it consumes. So I would say, if it's done right, it can be a carbon neutral case. I have also here, I just skipped some slides because it's more or less the same, but just another example of a system where you can utilize. Here's a field, and this field is covered in solar panels that produces hot water. Underneath the blankets here is a pit. And during the summer, this 6 megawatt system is using all the energy it can from its solar panel, but it could also be a waste heat from a process industry that produces waste heat all year round. This is put into a storage, a pit. I have seen some examples where you're using old pits created from sand. When you use sand and you create an artificial pit, it's stored here in a basin, a water basin. It has an efficiency of 78%. So this city here actually produces, storing energy from the summer, putting it into the pit. And then during the winter, they run the heat pump here on ammonia. When they have used all the energy in the pit, they move to ambient air heat exchangers. Or if it's a better COP using the ambient air, they use that instead of the pit. This city, in combination of solar panels, pit, ambient air heat exchangers, has a 97% carbon neutral footprint compared to if they had used their old source that was natural gas. Yeah, I will spend the last, I think I have 3 or 4 minutes before we move into the questionnaires. I will just simply say total cost of ownership. This is a very simple example. Know your payback time, know your loan interest, calculate the heating capacity you need per year, and then compare different heat pumps. I have made 3 examples here, COP of 3.6, 3.2, and 3.7, 3 different investments. And the payback here actually means that heat pump number 2 with the lowest COP of 3.2 is actually the one giving you as a customer the best business case. And how is that? That's because when you're doing heat pumps, it's all about total cost of ownership. It's about service cost per running hour. It's CAPEX investment, but it is a business case. So as an engineer, we are always striving for the highest COP and the best equipment. But we also need to learn that sometimes this actually affects our business case. So in heat pumps, when I do heat pumps, I calculate maybe 10 or 15 different combinations of heat pumps, screws, recipes, serial, parallel operation, and then put additional heat exchangers, superheaters or subcoolers or whatever to extract as much energy to increase the COP. But every time I match the additional cost of the heat pump towards what do I gain in the total cost of ownership. CO2 savings is also very different. And as I said, remember that it's dependent on the country you come from and what is it, the electricity you are substituting. France, Norway, Sweden have, for instance, a very low carbon footprint. They use nuclear, they use hydroelectricity. Denmark use 50% of all electricity from wind turbines, but it's different country to country. So the CO2 saving, calculate that. And then the last thing, and that is really a surprise to many, and now we switch to Spain for some odd reason. But implementing a heat pump, taking away the water consumption on the evaporative tower, reducing the electrical fans on your condenser or your dry cooler, actually gives you a saving, a monetary saving, that in all the cases I have calculated, always is bigger than what is the annual service cost on the corresponding heat pump. So alone, remember to keep the savings that you get from water, electricity on your heat rejection plant, to calculate it into your business case, because it's not insignificant money you save on your evaporative condensers. Yes, I think, Michael, I'm about 1 minute past. I just have here, before we go into questions,
Sure.
I have a bucket list. I'm 52, and I hope to see 2050, because then I'm 80, and then Europe has an ambition of going carbon neutral. If I can live to see that, I will be grateful. But in order to achieve that, I put together a bucket list. And a bucket list for me is that in the next 5 years, we need to move heat pumps into 140, and in the next 10 years into 180, because that means we can substitute steam systems. And there are only natural refrigerants, in my mind, like water is by far the best. There are also other refrigerants. Ammonia is maybe super cool up to 100 degrees, but above 100 degrees, we can use CO2, we can use water, we can use all the hydrocarbons. But I think the boom that comes from power to X, all the electrolysis, all the that we will see here in the electrification, I think the future of heat pumps in the next decade, or until 2030, will move into above 100 degrees on heat pumps. Yes.
Okay, thank you. Thank you very much, Morten. That was a really great, very comprehensive look at heat pumps. And I think I have a few questions, and of course, the audience is welcome to put a question in the Q&A box if they have any in the remaining minutes here. The heat pumps you were talking about, were those all using ammonia as the refrigerant?
Yes, I'll just think, just a minute. So now you can see me. Yeah. So ammonia is a great refrigerant. I think one of the things that we also have learned with introduction of heat pumps is that I'm actually in favor of all heat pumps, no matter the refrigerant. The thing is that using ammonia as a refrigerant gives you the best efficiency. It gives you not that I'm putting towards other refrigerants any bad spell on them, but ammonia in the range from 65 to 100, it's it's it from 65 to 100. They are kind of superior, and it's especially if you go into a double two-stage and you use economizers and so on. And as we started with heat pumps, the pivot with the ratio between the electricity price and the fuel cost was very high. So that means the first heat pumps was actually ammonia, because they was the only one who can achieve the positive business case. So that's why we have used ammonia so much. Fortunately, now I see also CO2 heat pumps joining the market. I would think in the low tonnage propane or isobutane hydrocarbons are fantastic also. So all the natural refrigerants has a preference here, but in industrial equipment, ammonia is good. We have, of course, also as refrigerant companies, refrigeration equipment companies, we also have a deal here, because there's a sustainability push in the but there's also a push towards environmental and especially health and safety for workers. So for using ammonia, we have to also now to invest some money, at least from my perspective, in low charge systems, because you cannot be blind to the fact if you have a district heating center sitting in a highly urbanized area, it's maybe not cool to have 5,000 kilos of ammonia, but if you can use a spray chiller evaporator, or you can use a microchannel evaporator, and you can reduce that by a factor of 5 or 10, then it becomes more edible. If you have ammonia chillers, it develops scrubber systems that can capture any leakage. So yeah, ammonia is fantastic, but we cannot sell it only on the fantastic thing. We also have to ensure our customers that is safe to use, and I think that's a task that goes on top of the good business case. Yeah.
But the case studies you referred to were using ammonia in the
Yeah.
And with those, what was the charge of ammonia for those relative generally with those?
Yeah, for a system like for a data center where you produce 27 megawatts or 27,000 kilowatts of heat, there's a total of 9 machines, and they have on average 250 to 300 kilos of ammonia. Mm-hmm. So it's really not that much. It's less than 3 tons for 27 megawatts. But on the other hand, if you go into systems like the ambient air heat ambient air heat absorbers, a 6, then it's maybe 1 kilo per megawatt. So a system where you take the energy from the ambient air, it's maybe 1 kilo per kilowatt. So it's 1,000 kilos per. So that's where I think we need to move into microchannels, or do whatever we can do best to capture, because at the end of the day, ammonia is a good refrigerant. It will always have a low price. It's relatively sustainable also in production. So I think it will have a future. But we as that work with this kind of technology also need to face the fact that some see a challenge in the environmental, especially health and safety, with the large charges. But you can mitigate it. Yeah. You can put it in industrial areas. You can move it outside the. Right. So there are many ways to deal with it, and that will be necessary. Yeah.
Are these being marketed in the U.S.? These ammonia heat pumps?
Yeah, I would say in North America, you have had a tradition for inexpensive fossil fuel for many reasons. But I was actually watching the day I was watching President Biden, his first day as a president. At my Teams chat appeared Bob from York in US, one of my dear colleagues, and he said, "Now it starts. Now it's also starting here with us." So I think you have a great future in North America for heat pumps, and with a very high number of production sites and so on. Also, what I see is many of the cases we have covered here is actually for district heating, and I'm seeing a huge interest in North America for district heating, really booming, and also not only district heating but also large campuses like universities and hospitals and office areas that is utilizing the benefits of a district heating and district cooling system. So yeah, it's coming in North America as well.
Okay, great. Yeah, we'll looking forward to that, because yeah, there certainly is a lot of interest in the decarbonization in the states, particularly California, but other states as well. So the opportunities for ammonia heat pumps would definitely be there for JCI and other companies from Europe to bring them over. Yeah.
Yeah, and not only because it's more or less hot enough in California almost all year round. But again, when we're moving into electrification, we are moving into power to X, where we use solar or wind turbine, and we need to produce liquid hydrogen. We need to use electrolysis, and we need to maybe create systems for carbon capture. And in all these processes, you can actually increase the efficiency of the system by utilizing heat pumps as well. So heat pumps do not only play a role in food and beverage. Yeah, they do. They also play a role in district heating. But the emerging sector that we are seeing with the global electrification will be the third wave of the first wave of heat pumps was district heating. Second wave is food and beverage, and the third wave of heat pumps will be high temperature heat pumps utilized in steam processes, in electrolysis and power to X systems. So a bright future, even in California, where we don't have district heating.
All right. Well, with that, we're going to close the session. Thank you so much.
Yeah,
Morten,
you're welcome
for that, and staying up late in Europe for us. We really appreciate that.
That would not be the first time. So
okay,
always a pleasure.
And if there are any other questions for Morten, you can reach out to him through email. And with that, we'll close the session. Thank you very much.
And thank you all for taking the time to be on it. Was a